Thank you, Mr. Chairman. I really appreciate the introduction. And I would like also to thank the organizer, especially Dries, Diva, who invited me to share with you some of the work we're doing at Argonne National Lab. I'm very sorry I can't stand in front of you because I broke my leg, so I'm in the recovery process, so please excuse me. Today I would like to share with you some of the work on developing advanced chemistries for automotive application. That's the task that we were given by the Department of Energy, and Argonne is the leader in this area. I have talked to my colleagues on the way back here, and I was told I have to put some more business information as well, at least to show you that the phosphate material has a big future in this field. Okay, so I'd like to start with this busy slide. This is the 2009 Global Human Activity Energy Flow. The message here is very clear. All applications, either residential, commercial, or industrial, rely on many sources of energy, as you can see here, from hydro all the way to natural gas and oil. There is one application, which is transportation, that rely on one source of energy, which is oil. And the story doesn't end up here because half of the energy is wasted in heat. So not only we are relying on one source, but we also, not only on our source, but we waste half of it. So this situation is very unsustainable, obviously, in the future. So this is one of the main reasons why we have to think about electrification of vehicles. There is another reason, which is, at least in the United States and China and in Europe, United States basically consume about 20 million barrels a day of oil, and 72% of that goes to transportation. So if you really want to make an impact, we have to make sure to accelerate the commercialization of electric vehicle. And another thing which is more of a general concern of all of us is greenhouse gas emission, as you can see here. This is the CO2 reduction glide path in a long term. So if you stay as business as usual, you will see that within 100 years, the atmospheric CO2 concentration can go to 700 ppm. And that translates in almost 4-degree increase in the Earth temperature. So now you can really think about some real climate change. So if we make electrification as our mission, we should be able to stabilize this number to where the industrial countries has agreed on. It's 450 ppm at the Kyoto Protocol. Now, fortunately, electrification is underway. And here is one reason, is basic regulation. In the United States, there was a law that passed during Obama administration that mandated 54.5 miles per gallon. I'm not sure this law will stand now with Trump, who is more of an oil and he's not really a believer of the climate change. So, but Europe and China are very aggressive and moving forward. So you have Europe, which is giving 58 gallon per mile per gallon by 2020, and China, which is obviously because if you go to China, you can see the reason why the pollution is just unbelievable. So they are making a big effort in trying to address this. And the great things about China, this is very powerful, I would say, government. So if they say things, it will happen. So, and they have actually mandated 56 miles per gallon by 2020. So, and I see because of these two, United States has to follow. Because most of the car industry in the United States make more money in China than in the United States, like GM and Ford, for instance. So I don't see any return to dirty technology from the energy point of view. Also, I have to give a lot of credit to Toyota Motor Corporation because they are the one that started the commercialization of hybrid electric vehicle. This is a very simple system, and that's the reason why you see tremendous acceleration of commercialization of hybrid in Europe and in the United States. And the reason is because you have a very small battery that you add to the vehicle. You still have an electric motor, engine, and a tank. The battery will mostly assist the main engine during acceleration, but most importantly, it will recover the energy that you usually waste in heat when you brake and charge the battery. So that's one of the reasons why this system is low cost, because the added cost of the battery is very small. And you can buy now a Prius for $19,000, for instance. And I think the expansion of Prius and other technologies from other companies has grown significantly to millions of vehicles now. In the United States, our target is the plug-in. The plug-in, as you can see, you need to have very large battery. And this battery has to be able to allow you to go all electric to your work and come back. And if you change your mind, you can apply the hybrid system, so you can use basically gasoline coupled with the electric motor. So because of that, you have many technologies. You have an internal combustion engine, you have an electric motor, you have a very large battery, you have a transmission, and you have a tank. So for that, the amount of technologies within a very constrained volume is very, very high. And therefore, the energy density requirement for battery is very, very severe. It's actually more severe than electric vehicle, where the battery is the brain of the vehicle. Basically, you don't have anything else. So here we are targeting 40 miles because in the United States, 75% of the commuter commute within 40 miles. And that's very, very challenging. The applications are very significant. You have lithium-ion, for instance, has dominated the consumer electronic. The next big application is the vehicle, electric vehicle, and the grid. So you go from watt-hour to kilowatt-hour and megawatt-hour. So there is a tremendous amount of expansion for the people who are developing, for example, materials that goes in batteries. This is just a forecast of the hybrid and electric vehicle in the world. You can see different forecasts. Some people are targeting, for example, within this is very old, 2014, there will be 2.5 million. And I think this is very conservative because now the hybrid, there is more than 5 million vehicles in the market, if you take Prius and GM and others. So very conservative forecast. On electric vehicle, by 2020, you expect 5 million vehicles. And those are large batteries that goes in electric vehicles. So tremendous amounts of material will be needed for this application. And here is the growth of plug-in and electric vehicle sales so far up to 2015. You can see between 2014 and 2015, the plug-in has went up by 48%. Now, the amount of vehicle is very small. It's only 250,000 vehicles, absolutely, comparing to 80 million vehicles that get produced and sold every year. A big chunk of that is in China and Europe and the United States. So you can see China is really dominant because the government is putting tremendous amount of subsidy and funding to advance the technology. On the electric vehicle, the growth is about from last year to this year, 2014 to 2015, is about 61%. And as you can see, China is the dominant. The good news is China is using iron phosphate, which is something that of interest to OCP. So there is an opportunity for a big business here. This is the worldwide battery market. It's about $65 billion. Mostly is in consumer and storage for, how to say it, the lithium ion here is eventually taking over the nickel metal hydride batteries because the big chunk of the batteries for nickel metal hydride goes in the Prius for hybrid electric vehicle. So once they switch to lithium ion, you see tremendous opportunity for lithium ion market-wise, actually. And these are the application. And you can see, for example, for automotive, it's still very small. There is a tremendous amount of growth in the future. And these are, for example, as I mentioned, the different applications. You see the automotive is here, the portable and other applications are the biggest business at the moment. So we expect within the next 10 years, the automotive business will grow significantly with the opportunity of reducing the cost. Obviously, you will see tremendous growth in hybrid and plug-in hybrid and electric vehicle. And this is regarding specifically to lithium ion. You can see at the moment there is almost production of 5,600 million cells at 60,000 megawatt hour at the moment. So, and these are mostly consumer electronic, laptops and computers and so on. The battery for automotive is still very small. I say it's mostly dominant by China which is really the leader in this area at the moment. Now, as I mentioned, lithium-ion is very attractive because it provides the highest volumetric and gravimetric energy density. In another word, you can make batteries smaller, lighter, but yet very energetic. There is a big, square here, which means the technology is very versatile. You can develop different cathode, anode, electrolyte, different system, high voltage, low voltage, and so on. Unlike this system, which basically the chemistry is very fixed. You just have some dopant to improve the performance. So there is an opportunity here. And for people who doesn't know what is the concept of lithium-ion, I have a small schematic representation. You know, the lithium-ion has a cathode which has a layered structure where lithium is sandwiched between metal oxide slabs and has carbon as the anode. Carbon also has a lamellar structure. So during the charge, lithium will move and will be conducted through an electrolyte, which is a non-conducting media, and intercalate into carbon. And the electron will move this way. And then during the discharge, the lithium will go back. What happened? So basically, it will go back, and then the electron will go and basically power the device. It's very simple. So it's a very simple concept, but when you charge these electrodes, they become extremely reactive. So what happens is you have tremendous surface reactivity, which are very difficult to understand and make this system really very complicated. So stabilization of these material will alleviate this problem. So these are the major components that are commercially available now. You have the layered oxide in consumer electronic. We've seen now some penetration in automotive. You have the spinel, which used to be the introduction by GM for PHEV volt because it has some safety consideration. And then you have the iron phosphate, which is mainly dominant by the Chinese in mostly electric vehicle and electric bus, which is a very big program. And as I mentioned, the carbon is the material of choice for anode in this case. So you can see, for example, the iron phosphate has lower voltage, fairly decent capacity. So some of these materials shows much higher capacity than the iron phosphate, but as I will show you, this material has outstanding safety characteristic, and that's the reason why it's used in large format battery for buses and electric vehicle. So obviously there is still some work to be done. So there are some key barriers. One of them is safety. You need inherently safe battery, and the other one is cost, because people need to be, the technology need to be affordable. So let me show you one video. Can you click on this one? I'm not sure if you can. I don't think so, you hear me. Can you click on this? Hello? It's okay. So you can see once you have a nail penetration of a 10 amp hour cell, actually, which is for hybrid, nothing happened. There is barely any evaporation of solvent, so the heat is very minimal. This is an industrial way of testing. Now, if you take, for example, the NCA, which has high capacity, this is a smaller cell, so the amount of energy is smaller than here. This one is using a Tesla Motor Corporation vehicle. So please click on this one. This is what you get. Because this cathode is extremely reactive when you remove lithium. You have nickel 4+, which is unstable in an oxide phase. So you have an immediate decomposition and generation of oxygen that react with the electrolyte, which is extremely exothermic. So you end up with a thermal runaway. And that's the reason why the Chinese are using this system, because of its outstanding safety characteristic. And one of the reasons is because the PU bond is very difficult to break up. So there is no oxygen release in this case. So it brings me to the iron phosphate. I'm going to mostly focus on the iron phosphate. As you can see, it has many benefits. You have phosphate and iron. These are the cheapest element. So cost-wise, it's very attractive. The PU bond is very stable, so there is tremendous amount of stability in the material itself. And I just show you the thermal safety is outstanding in a real test using a hybrid battery cell. It has a lower potential comparing to the oxide, but not that low. 4 volt versus 3.5 volt. capacity is fairly high, similar to the oxide. So the advantage here, when you remove lithium, you charge iron from 2 to 3. And iron 3 is the most stable form of iron. So you don't have reactivity with the electrolyte. When you go higher in oxidation state, the reactivity goes up. So these are all very attractive characteristics, but the problem, it has very poor electronic conductivity. This is a serious issue, because if you really want to move lithium through the particle, it will be very difficult, and therefore you cannot achieve good performance. And one way to address this is to use nanomaterials. So basically you reduce the pathway of diffusion within that particle. So when you do that, what happens is you create an issue of density. The packing density of the material becomes very low, and therefore the energy drop. So what I would like to show you today is there is an area, an idea to fix this problem. Before I go, I just show this slide that I took from one of the study. This is in 2014. 2013, you can see the cobalt oxide is a dominant for consumer electronic. The iron phosphate was very small, 8%. And by 2015, you can see, because of the expansion of electric vehicle in China, it went in from 8% to 23%, and the expansion is growing at 8% a year, basically. So there is an opportunity with this material. Now, you can make this material with different ways: solid-state reaction, ball milling, carbothermal reduction, hydrothermal, which is very dominant now, and spray pyrolysis. I'm going to show you that this could be an interesting opportunity to make very dense iron phosphate to take care of the energy problem if you increase the density. Here is one example that just to show you the importance of nano and also carbon coating in improving the performance of iron phosphate. So in this case, we use this type of precursor mixed with lithium carbonate. You calcine, and you do a second calcination, and then you end up with you do a carbon coating, obviously, and you end up with a green powder to black powder. I'm going to show you how to do the carbon coating. A lot of people use polymers or carbon mixing. Here is a much clever way, which is using propylene or toluene, because it's a gas. Gas go everywhere, so you basically can end up having contact with all the particles, not just surface contact if you do a normal mix. And you can do that easily at very low temperature. You crack basically propylene and you form carbon at the surface of this nanomaterial. Here we have basically a particle that is 300 nanometer that give you fairly good performance, because the pathway of lithium diffusion has been shortened. So it's much easier to move lithium out than if you have a micron type particle like in the oxide, where the density plays a very good role in energy. But unfortunately here, if you use nanomaterial, your density is very, very low. You can't pack active material in the electrode and therefore in the cell. So that's a challenge for the iron phosphate. Because if you have low energy, you have to put more barriers, and that increase the cost of the full pack. So to understand how much carbon we put with the cracking, you can just use a TG. It's very simple, TGA. If you basically heat up the iron phosphate, you basically oxidize it, you form this phase, which is a trivalent iron, and that the associated gain weight theoretically is 5%. Now, if you have carbon there, so once you do the same things, you increase you basically increase the weight, and once you start burning carbon, you drop the weight, and the difference is the amount of carbon that you have in your material. It's very simple. In this case, we have about 2%. In general, when you have nanomaterial, you have to put 10 to 15% of carbon, and that also can affect because you put in inactive material in the electrode, and that affect the performance of the cell. But with this clever cracking of toluene or propylene, you can put very tiny amount of carbon, less than 2%, and the performance is very outstanding. This is an X-ray that shows that the coating does not affect the overall bulk structure of the material. As you can see, before and after is exactly the same things. But if you look at the impedance, which is very important for power, you can see, for example, if you use a Canadian company that sell this material, they use about 10%, the impedance is very high. If you use, for example, most of the industry is using iron phosphate with 15% of acid and black, you basically, because you increase the carbon amount, you get more contact, electric contact, the impedance drop. But with our process, we use only 2%, so the amount of iron phosphate is much larger here. You get much lower impedance, so therefore more power. So because gas-solid reaction is the best way to create a good protection and good surface coating. And performance-wise, the material performs very well at high temperature and room temperature, and this is in a full cell. We have data that shows thousands of cycles. I couldn't find it because it's a little old. But the bottom line is when you do a nice carbon coating, you can get very high rate capability with this material. Now, nanophase, as I mentioned, can deliver significantly high power, but the problem is the poor packing density, as I mentioned, because it's nano. So that basically results in lower energy because you don't pack as much active material as you need. So how can we address that? And here is an example that shows a battery, how big it is. This is the dimension of the battery. It's 18650. The capacity is only 1.1 amp hour. And if you take the lithium cobalt oxide, which has about 5 times more density, practical density than the iron phosphate, a tiny battery gives you more than 2 times the energy. So that's the problem. So the idea is how can we address the density to increase, you see, it's 1 gram per cc versus 2.6 gram per cc density-wise. So we need to bring this material higher to increase the density, increase the energy density, so you can reduce the cost and make this technology much more expandable for electric and plug-in. So, and to do that, we decide to go with a new process. It's a co-precipitation. We want to synthesize micron-size iron phosphate. So if you do that, obviously the pathway diffusion become very long and the performance will drop. But we want also to put in a clever nanopores through the particle. So, and I will explain why it's important. To make this material, this is a process that uses phosphoric acid. I know that the OSOP is the largest producer of phosphoric acid, so there is an opportunity with this. And you use a cheap iron 3 type nitrate material. You put it in a reactor, you use a chelating agent and co-precipitating agent, and you form this phase here, and basically you dry it, you filter it, you form FePO2, and then you lithiated it. And then you do the carbon coating using the process I show you. So this is how it looks. Its material is spherical, as it showed from here. So obviously it's 5 to 6 micron, in some case 10 micron, so we're talking micron size now. But when you do the cross section, you get like a brain type morphology. So we created nanopores across the particle. And the idea is when you fill the electrode with the electrolyte, these pores will be filled with the electrolyte, and therefore lithium here, instead of going all the way here, it will come here and fly very fast out of the material. So you should expect very good power capability without affecting, you should get very high energy without affecting the power performance of this material. And of course you can do the coating, as I mentioned. This is, you can do coating at the surface and within the pores. And the best way to do that is cracking propylene or toluene gas, because gas go everywhere before you can basically decompose it. As you can see, we have carbon at the surface of the particle and carbon inside the pores for better conductivity. And this is a PMA that shows the carbon is everywhere, not only at the surface of the particle, but inside the pores as well. So how about the performance? So this is the gravimetric energy density of a 200 nanometer iron phosphate versus 6 micron. Obviously it's gravimetric, the capacity is the same. But look at the volumetric, where the density play a big role. You can see we almost double the volumetric energy density. Now we are very competitive with the oxide. And this material is not commercially available, so I'm hoping we can do it with the OCP folks and the R&D folks here. It will be very interesting. And you can see now we move from 100 milliamp hour per square centimeter to almost 250. So now that we can talk about some real density, you know, that are very similar to the spinel, for instance. So, and the volumetric density basically more than doubled in this case. So how about the power? Because that's very important. You know, if the power is not that great, then we don't have a case. And here is the gravimetric capacity versus C rate. When you go at very high rate, when you charge and discharge at very high rate, we're talking about, and this is with the nano versus micron. You see they're almost parallel. Very, very close. So we did not affect the power capability of this material. And this is the volumetric capacity when you do fast charging and discharging. You can see clearly that the energy is much higher with the micron size iron phosphate versus the nano. And the power performance is very, very, very good. It's just parallel, basically. So we did not affect. The bottom line is the performance is not affected because, as I mentioned, the lithium inside the particle doesn't have to go all the way out to the edge. It will just seize those pores, and then the pores are filled with the electrolyte, and the conductivity of lithium through the electrolyte is much faster than in a solid, where you have just a diffusion. Now, and here is the impedance. It's almost similar. So the bottom line is this material could be suitable not only for electric vehicle where the power is not very significant, but also for energy. Like in plug-in where both the energy and power are necessary in this case. And these are some of the performance at different rate and different temperature. As you can see, they are very, very acceptable and very similar to the oxide, which are used now in automotive application. And these are some of the cycling performance. As you can see, at different temperature, is very stable. It's very stable is because of the nature of the material, you know. Iron phosphate, as I mentioned, you oxidize iron to 3+, and 3+ is very benign to reactivity with the electrolytes. You don't see any surface reactivity that lead to impedance rise and degradation of performance. Now, this is good, but there is other opportunity to increase the energy and reduce the cost. And I will show you how to do that. I don't know how much time I have. Is it okay? Mr. Chairman, it's okay? Yeah. So one way of reducing the cost is to increase the energy, as I mentioned. Here is an example. If you take, for example, a pack that belongs to Nissan Leaf, for instance, is a 23 kilowatt hour. It's a 500 pounds and 125 liter. Now imagine if you increase the energy density of the chemistry inside this pack. What will happen is you can still design your 23 kilowatt hour, but your pack becomes smaller, which means the amount of cell become less and the amount of material in the cells become much less across the board, active and inactive. Not only cathode and anode, but separator, electrolyte, and so on. And you can make some significant cost reduction this way. A lot of people in the academia, at least, they refer to iron phosphate as a cheap material, and therefore the cost is low. This is very misleading because the cost of a cathode in a pack is only 10%. So if you remove completely the cathode, you reduce the cost by 10%. You don't have a battery anyway. But if you do it this way, you reduce the cost across the board. You see, we reduce the weight by almost half. And that's really cost, because these are materials, including inactive like current collectors, copper, aluminum, separator, and so on. So we really need to increase the energy. Now, I have shown you how to increase the energy of the iron phosphate by designing unique morphology. But there is also an opportunity by increasing the energy, either by increasing the capacity of the material or increasing the voltage. So fortunately, there are many other phases of phosphate that have high voltage. One of them is manganese phosphate. Manganese is still cheaper metal. As you can see here, it's a 4-volt system. So now you jump the voltage by 0.5 volt and you increase the energy significantly. And you can do the same process to make dense nanopores type material. This is an example that shows the co-precipitation. So basically you take the precursors, mostly nitrate, which are very low cost, and then you add a phosphoric acid, and you create a chelating agent and co-precipitating agent, and you co-precipitate your material, and then you treat it with a carbon coating, and you end up with a black type powder that is carbon-coated manganese phosphate. It's very simple. As long as you control the conditions. So there is an art of parameters that need to be controlled to get where you want. And you can see here now we have a 4.1 volt, almost 4 volt. This is basically related to the iron that get oxidized. The reason is manganese phosphate is extremely insulating. It's like an order of manganese more insulating than iron phosphate. So having a little iron does help, as you can see, if you compare the micron versus nano. And volumetrically, you can see you have almost 50% increase in the energy density. So it's still very attractive. I'm almost done. And cycling-wise, you can see the capacity is much better. This is the volumetric energy density. We gain almost 50% energy density by using this concept, and also gaining more energy by pumping the voltage higher comparing to the iron phosphate. So there is an opportunity here. And there is also cobalt. Cobalt is not very applicable in automotive, unfortunately. I didn't want to put it here because it's very low, high cost. If you add cobalt, lithium cobalt phosphate is a 5 volt system. So the energy-wise will increase significantly, but it's not very practical for automotive because of the cost of cobalt. It's very, very significant, and that when you expand the production of cobalt-based phosphate, the cost will goes up, and that can defeat the purpose. But manganese is very attractive, so there is very little work has been done on manganese. There is more work to be done, and I encourage you guys to look at it, at least the people who are working on phosphate material. Now let me show you the safety of this material also. Sir, can you click on this? So this is this is a 5 amp hour manganese phosphate based cell that one student was crazy enough to start poking out with a nail. So I wouldn't recommend you doing it. Can you? Hello? Yeah, you can see this is very dangerous. I mean, the guy is very brave, I would say. So he's basically poking this cell, which is fully charged, highly energetic. You can see there is some vapor because of the heat that gets generated that evaporate the electrolyte, but overall, he's very insisting. That's one of the reasons. So if we are able to design manganese phosphate that work like this, I think we'll be in good shape. I wouldn't recommend student to do this. Yeah. But he was confident. He ran all the tests and he didn't see anything. Say, okay, I'm going to abuse it myself and see what happened. Yeah. And so my conclusion to you is really, if you have to enable future electrification, we really need to develop safe and high energy system. And I've shown you at least what the community here is interested to. There are opportunities of using phosphoric acid to make very, very promising and material that is high energy through the design of the structure where we have micro-sized particle that has nanopores, where you can impregnate the electrolyte in the pores and increase the power without increasing the energy without compromising the power. I've shown an example of the iron phosphate, and also the manganese phosphate is very attractive as well. Thank you very much.